A farmhouse window in rural Norway. The glass is original, the putty is original, the year stamped in the parish record beside it, 1887. That single window has outlived 6 generations of the family who built it. Meanwhile, your modern synthetic window seal, the one the hardware store swore by, cracked within 5 years. In a cold climate. The modern sealant industry sells you a product designed to fail. That is not an accident. But there is another way. 2 natural ingredients. 1 $12 mixture. A method practiced since the 1700s. As a Norwegian craftsman named Sven once put it, your grandparents didn't have a hardware store. They had something better. They had a recipe. And that recipe is what we're here to talk about. Picture Scandinavia in January. Temperature drops to -20 Celsius. The ground freezes hard as iron. Moisture seeps into every crack, every hairline gap, every place where wood meets glass. Then, without warning, a thaw arrives. The wood swells. The glass shifts. The seal is tested again, and again, and again. This cycle repeats for months, every year, for decades, for centuries. There is no harsher testing environment for a window seal on Earth than a Nordic winter. The wind drives sleet horizontally into the frame face. Ice forms inside the groove itself, expanding with a force that splits stone. And yet the seal holds. And yet, 19th century Swedish and Norwegian builders had absolutely nothing we would recognize today. No silicone cartridges, no foam backer rods, no synthetic compounds engineered in a laboratory. The hardware store did not exist. The supply chain did not exist. What they had was chalk, linseed oil, and the accumulated wisdom of generations who had already failed and corrected and refined before them. Every mistake had already been made. Every bad ratio had already cracked. What survived into the written record was only what worked. Necessity forced a solution. And that solution was a natural putty, one that did not fight the window frame, but moved with it. This is the key principle that modern sealant manufacturers quietly ignore. Elasticity beats rigidity. Every time. A seal that breathes, that flexes, that expands and contracts alongside the wood it bonds to. That seal survives. A seal that stiffens, that grips too hard, that refuses to yield when the frame shifts, that seal cracks. It does not matter how expensive it was. It does not matter what the label promised. Rigidity loses. The 2 ingredients at the heart of this method cost $12 combined. $12 total, enough material to seal 4 standard windows. That price has not changed in any meaningful way since this technique was first recorded. The ingredients have not changed either. What changed is that an entire industry convinced you to forget them. That ends here. Here's exactly how this is going to work. Number 1 on our list is the foundation of everything, the 2-ingredient secret itself, where it comes from, and why it has outlasted every synthetic alternative the modern world has thrown at it. The year is somewhere in the early 1700s. A Swedish farmhouse, deep in the countryside, far from any city. The carpenter standing at the window frame has no catalog to order from. No truck will arrive in the morning with a tube of pre-mixed compound. He has a bag of chalk powder and a tin of linseed oil pressed from the flax plants growing in the field behind him. He mixes them together on a flat stone, working the oil in slowly with a wooden paddle, watching the texture change from loose powder to something cohesive and smooth. He presses the result into the frame with his thumb. He moves on to the next window. No label, no instructions, no expiration date printed on the side. That moment, unremarkable, unrecorded, repeated in thousands of farmhouses across Sweden and Norway, is the origin of one of the most durable building techniques in European history. The 2 ingredients are whiting chalk powder and raw linseed oil. Whiting chalk powder is calcium carbonate in its simplest processed form. You can find it at any hardware store or art supply shop. Raw linseed oil, not boiled, not blended, raw, sits right beside it on the same shelf. The pair of them will cost you $12. That is not a rounding error. That is the actual price. The Swedish glazing tradition has a name. It is called fönstermålning, and it is documented in rural homes going back to at least the 1700s. The Norwegian parallel is known as husmåling, farmhouse sealing, and chalk linseed putty appears in farmhouse records and restoration archives stretching back through the 1800s. These are not folk myths. They are documented building practices, preserved in the same archives that record the dimensions of the houses themselves. Here's why the chemistry works, and why nothing the modern industry has produced has genuinely improved on it. Linseed oil polymerizes. Slowly, over days and weeks after application, the oil undergoes a chemical reaction with oxygen. It cross-links, it hardens, but not completely. It never reaches full rigidity. What it produces instead is a semi-elastic matrix, somewhere between a solid and a flexible compound, that binds the chalk particles together without locking them into a brittle structure. The chalk gives the putty body and bulk. The oil gives it life. Together, they create something that can compress under pressure, flex with the wood as temperatures change, and then return, slowly, partially, toward its original form. That behavior is precisely what a window frame needs. Wood is not static. It absorbs moisture and expands. It dries out and contracts. A frame in a Nordic climate can shift measurably between January and July. A rigid seal cannot follow that movement. It fractures at the weakest point, and moisture enters through the fracture, and the failure accelerates. Linseed chalk putty follows the frame. It does not fracture, it simply adjusts. The heritage proof point is not theoretical. In Copenhagen, 18th century Danish buildings still carry original linseed putty in their window frames. Untouched, not restored, not replaced, original. Restorers who have worked on these buildings describe pressing a thumbnail into the putty and finding it still yields slightly, still holds the impression, still bonded cleanly to the wood beneath it. 200 years of Nordic winters, and the material is still doing its job. One of these saves you more than all the others combined. And this is it. Not the technique, not the timing, the material itself. Getting the two ingredients right, understanding what they are and why they work, is the decision that determines whether everything else succeeds or fails. You can apply putty perfectly and still fail if you substitute boiled linseed oil for raw. You can prepare the frame correctly and still fail if you use a calcium compound that is too coarse or too fine. The ingredients are not interchangeable with their near equivalents: whiting chalk powder and raw linseed oil. Those exact materials. That is the sentence that matters. Danish putty that is still pliable after 2 centuries. A Norwegian farmhouse window, seated in 1887, still holding glass in its original glazing compound. That is not a coincidence. That is not luck. That is a recipe that was correct from the beginning and has never needed to be replaced, only remembered. If that one surprised you, the next one is bigger. Coming in at number 2. The mixing ratio. Because knowing the ingredients is only half the answer. Get the proportions wrong, and you will have an expensive failure sitting in your window frame within a single winter. The ratio is 2 parts whiting chalk powder to 1 part raw linseed oil. By weight. Not by volume, by weight. This distinction is not a minor technicality. Chalk powder and linseed oil have different densities. Measuring by volume produces an inconsistent result every time. A kitchen scale, a postal scale, a basic gram scale from a dollar store, any of them will do. 2 to 1 by weight. That is the entire formula. Now here is what happens when you deviate from it. Too much oil. The putty never cures properly. It stays soft and tacky days after application. In warm weather, it sags out of the groove, leaving gaps at the bottom edge of the frame where water runs freely. It picks up dust and debris from the air. It never develops the semi-elastic skin that protects the inner compound from UV damage. An oil-heavy putty is not a slow-curing putty. It is a permanently compromised one. Too much chalk. The putty becomes brittle. It loses the elasticity that is the entire reason this method works. Press it into the frame, and it will look correct for a season, maybe 2. Then the first hard freeze arrives. The frame contracts. The putty, rigid, inflexible, overdosed on chalk, does not follow. It cracks along the bond line. Moisture enters. The bond breaks. You are back to the beginning, except now you also have water damage behind the frame. That's not a typo, by the way. 2 to 1, by weight, is genuinely the single variable that separates a putty that lasts decades from one that fails within a year. The same 2 ingredients, the same frame, the same application technique. Change only the ratio, and you change the entire outcome. 19th century Nordic carpenters did not have gram scales. They developed a physical test instead. Mix the putty, then roll a small piece between your palms into a short cylinder. Press your thumb firmly into the center. If the thumbprint holds clean, sharp edges. If the walls of the impression stand without slumping, without crumbling, the ratio is correct. If the edges slump inward and the surface feels greasy against your skin, there is too much oil. If the edges crumble and the impression collapses into powder, there is too much chalk. The thumbprint test takes 5 seconds. It has been calibrated by generations of craftsmen who could not afford to get it wrong. The correct consistency has been described in restoration literature as resembling firm bread dough. Smooth, slightly tacky to the touch, but coherent. It holds a shape when you roll it into a rope. It does not stick aggressively to your hands. It does not crumble when you bend it. It yields under firm pressure and holds the form you give it. When you press a rolled rope of it against the back of your wrist, it should leave a faint impression without tearing or smearing. That is the texture you are working toward. The best one here is near the end, and it's worth the wait. But this ratio, this 2 to 1 by weight, is the load-bearing number underneath everything that follows. Every subsequent step in this method depends on arriving at the frame with correctly proportioned putty. Application technique cannot rescue a bad mix. Preparation cannot rescue a bad mix. The ratio is the foundation. Get it right before you touch the frame. And that's not even the costly one. This next one is. At number 3. Frame preparation. The step that every modern how-to guide glosses over in a single sentence, or skips entirely. The step that is, quietly, the reason most DIY window repairs fail before the putty even goes in. There's one on this list almost nobody knows about, and this is it. Not because the information is hidden, because it is boring. It does not involve a clever mixture or a satisfying technique. It involves scraping out old putty and wiping wood with oil. Nobody films that part. Nobody writes the headline about it. And so generation after generation of modern DIYers skip it, press their fresh putty into an unprepared groove, and wonder why the seal fails by the following winter. Here is what preparation actually requires. Remove the old putty first. Use a wooden putty knife, not a metal one. This is not a preference. It is a structural decision. Metal tools gouge the wood fibers of the frame groove. They dig channels and furrows into the surface that look minor but destroy the seal bed. The putty needs a smooth, consistent surface to bond to. A gouged surface creates air gaps beneath the new compound before it has even cured. Use wood. Work slowly. Lever the old putty out in sections, starting at the corners where the bond is typically weakest, rather than scraping aggressively along the length of the groove. At the corners, where two edges of old putty meet, work the tip of the wooden knife gently into the seam and rotate rather than drag. The old compound will release in a single piece, rather than fragmenting into dust and debris that embeds itself in the wood grain. Once the old material is removed, clean the groove completely. Every particle of dust, every flake of old paint, every trace of dried oil residue from the previous application. Work along the groove with a dry natural bristle brush, then follow with a clean dry cloth pressed firmly into the corners. Any contamination sitting between the new putty and the bare wood will break the bond. The putty will adhere to the contamination rather than to the wood, and the contamination will eventually detach, and the seal will fail. The groove must be bare, clean wood before anything else happens. And somehow, it gets worse. Because cleaning the groove is not the last step before application. It is not even the most important step. The most important step is one that Nordic carpenters have performed for centuries, and that modern guides virtually never mention. Before pressing any putty into the frame, wipe the bare wood of the groove with a thin coat of raw linseed oil. A light coat, not saturated, not pooling, just enough to darken the wood surface evenly. Use a folded cloth or your fingertip. One pass along each face of the groove. This is the primer coat, and it exists for a precise chemical reason. Bare, dry wood is absorbent. When you press fresh putty against it, the wood immediately begins drawing oil out of the putty compound. The linseed oil migrates from the putty into the wood fibers, leaving the putty chalk-heavy and oil-depleted at its base, exactly the conditions that cause brittleness and cracking. The primer coat saturates the surface wood fibers in advance. It fills the absorption capacity of the wood before the putty arrives. The putty then cures evenly, from surface to base, at the same rate, with the same oil content throughout. Skip this step, and the putty dries unevenly. The base layer, robbed of oil by the thirsty wood beneath it, becomes brittle within one season. The surface layer, still oil-rich, remains flexible. The two layers cure at different rates, develop different elasticity, and eventually delaminate. The seal cracks from the inside out. You will not see it happening until moisture has already entered. The next one costs almost nothing and saves the most. But before you move to application, the timing of the primer coat matters as much as applying it at all. After wiping the groove with linseed oil, wait 30 minutes. Not 20, not 5. 30 minutes, allowing the oil to soak fully into the wood fibers and begin its own initial polymerization. Pressing putty into a groove that is still wet with fresh oil creates a boundary layer, a slick interface, that weakens the bond. 30 minutes of soak time produces a primed surface, not a wet one. That distinction is what separates a seal that lasts 5 years from one that lasts 50. That one was simple. The next one saves you even more. Roll the putty into a thin rope, pencil thickness. Match the length to each edge of the window, cutting one section at a time so nothing dries out while you work. Press it into the frame groove using your thumb. Not a knife, not a tool, your thumb. Working from the corner outward in one continuous motion. No lifting, no gaps, no air pockets. An air pocket is not a minor imperfection. It is an invitation. Moisture finds air pockets. Frost expands inside them. The seal fails from within invisibly before you ever see a crack on the surface. As you press, you should feel the putty compress slightly and spread to fill the full width of the groove. If you feel resistance, the groove is not fully primed. If the rope tears rather than compresses, the mix is too chalk heavy. Both problems are fixable before you move to the next edge. Smooth the pressed surface with a natural bristle brush dampened lightly with raw linseed oil. Draw the brush along the putty face in a single direction, not back and forth. This creates a thin, continuous skin across the exposed putty surface. That skin slows the cure rate at the face and prevents the fine surface cracking that appears when putty dries too fast in direct sun or dry air. It also gives the finished surface a clean, slightly burnished appearance that takes paint evenly. Then wait. 7 full days before painting. 7 full days before rain exposure. Not 3 days. Not 5. 7. The patience here is not incidental. It is structural. The polymerization process that gives linseed chalk putty its semi-elastic character requires time. Interrupt it too early, and you interrupt the cure. The putty will never fully develop the mechanical properties that make this method worth doing. That farmhouse window, seated in 1887, still holding after 6 generations of Nordic winters, it was not pressed in and painted the next morning. Whoever applied it understood that the waiting was part of the work. They understood that a seal built on patience outlasts a seal built on speed. Every time. That 1887 window is still there, except now you know exactly why. Watch this next video to keep the seal lasting.